All right. This is going to be or serve as an introduction to circles, and a lot of the segments and lines that help us understand circles. Okay, and it's going to be probably a lot of information that you have not seen before. Okay, so well, it's a different it's the same, but a different kind of perspective of looking at it. Before we get into anything, it is important for us to understand what the definition of a circle is. Okay, um, I'm going to take a segment. Okay, it can be any length that I want it to be. Okay, so I'm going to take a segment. I'm going to make it a length of 5 here. And I'm going to create this A, and the A and B can be anywhere they want to be. But I'm going to make a point that does not move. Okay, I'm going to just say this is, maybe I name it my given point. Okay. I didn't do it the way I wanted to do it. So. All right, so that's the given point A. Okay. And B is a point that is 5 units away from A. Okay. So B can be there because it's still 5 units away from A. And then let me show that distance here. Let's put, all right, so 5. Okay. So B is anywhere that it wants to be as long as it's 5 units away from A, which is obviously the red point there. So if we do that, if I just trace those number of infinite points that are 5 units away from A, it provides those points there. Okay. Each one of those is a highlighted distance 5 units away from A. So that provides us the definition of a circle and how a circle is created. So we write that a circle is the set of all points equidistant from a given point called the center. Okay. In this case, our center is A. Okay. So we would refer to this as, using some notation here, we put a dot with a circle around it and capital A. So that's read as circle A, meaning that it's a circle with the center at A. The only number that defines that circle is the radius, where that's a little bit different than a lot of other shapes we've been dealing with. If I'm looking at triangles, we talk about how segment lengths, 3 segment lengths, 3 angle measurements kind of define a triangle, correct? Yeah. The only measurement that defines a circle is the radius. It's the only thing that you need in order to create a circle. Okay. Which is a real nice characteristic. There's a lot of other real neat, nice, convenient math. Okay. Sometimes, and this is just a vocabulary thing, sometimes this phrase here, set of all points, is referred to as a locus of points. Okay. Locus of point. Locus meaning set of. Okay. Or collection of points. So if you ever see that word, that's all they're referring to. There's a set or collection of points. So let's talk then about some other things about this circle. Okay, so we've got that circle. Obviously, that distance there, what do you call that red length? Radius. That's a radius. Okay, and again, that is the distance that's defining the circles, creating all those blue points. So now, when we look at a key line that is associated with the circle, and that key line looks like this. All right, that blue line, would you agree that it touches your circle only one time? Yeah. Okay. When you have a line that intersects a circle at one point and one point only, okay? So, this line, let me just put a couple different ones in here. That line, that black line, is classified differently than the blue one, okay? So, we're focusing only on the blue one and lines like the blue one, intersecting my circle only one time. Those types of lines are referred to as tangent lines, okay? So you need to write that definition down. A tangent to a circle is a line in the plane of the circle that intersects the circle in exactly one point. Okay, a lot of kind of key phrases that have been kind of mimicked throughout the rest of the course. In the plane of is a huge phrase for this definition. And then the word exactly is another key term. So incorporating those or leaving those phrases out will change the type of line or type of segment that we're dealing with. Okay. So those two things need to be met. The reason that exactly needs to be met is because of this idea here. If I do put, let's see here, if I do put this line in there, okay, does that line intersect my circle in one point?
Yes.
Yes.
No,
Okay. But the fact is that it intersects twice. Okay. But when I say that it intersects two times, it intersects one time to get to that, right? Does that make sense to everybody?
Yeah.
So that's why I've got to use the word exactly. So it takes this line and slides it out so it looks something like that. Okay. We cannot have it intersecting two times. Okay. So again, this is, let's see here, circle through B. All right, that red line is referred to as a tangent line, touching my circle at one spot. Okay. Now we can have portions of that as well. So what we mean by that is I can look at maybe that blue segment. We would refer to that as a tangent segment because it's a segment that touches my circle one time, right? Okay. If I look at, I don't know, something like this. Let's see here. Okay, that would be a tangent ray because it's starting here and it's going on in this direction forever, correct? Okay. Maybe I start there, okay, at that point where we're tangent, okay, and that would be a tangent ray. Now, would this be a tangent ray? Does that orange ray touch my circle? No. If I extend it, it does, okay, but just the portion that I have is not tangent, okay. Now it is, okay, and I can go, essentially any, like I said, any portion of that red line, as long as it's incorporating B, as long as it has B in it, is a tangent line or a tangent segment or a tangent ray. Is that okay with everybody? Okay. Now one of the neat features or one of the key theorems for tangent lines is that if I look at that radius and I look at my tangent line, they intersect. What type of angle do they form here when they intersect? A 90-degree angle. Okay.
Wait, how come you went to the top one? Oh,
It went 270. It went the other direction. So let's put a point there. So A to B to E that is indeed a 90-degree angle. And we see at that 90 degree, no matter what tangent line I look at, if I can move some stuff here, no matter what tangent line I look at, that is always a 90-degree angle, right? So that provides us a theorem, okay? And that theorem states, let's see here, if a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. Meaning you have a right angle at the point of tangency. The point of tangency is that point B that your line intersects your circle. Okay? So you get your tangent line, and the point where they intersect is the point of tangency. So your radius and your tangent line are always perpendicular at the point of tangency, which is really nice, and it's really kind of what ties in the tangent that we've already talked about in chapters 8 and 7 maybe, to what we're talking about now with circles. Okay? And I'll introduce that to you briefly, because I do think it's important for people to understand that though we've seen tangent, 3 or 4 weeks ago, using SOHCAHTOA and that kind of stuff, and now we're using tangent again, people think, well, they're different. They're not. They're really the same. But the way we're looking at them, the way we're dealing with them are a little bit different. When we talk about tangent or line, tangent line, we're talking kind of about this graphical image, but there is still a opposite over adjacent relationship here that we can talk about. Yes?
So I won't have to know like the tangent on my calculator and stuff like that
Yeah, you still need to be able to do that stuff.
for this chapter?
Sometimes, yeah. All right, so the reason this is referred to as a tangent line is because no matter what size my circle is, let me try to hide some stuff here. No matter how big my circle is, no matter where this point B is, you can see I can change the size of the circle. That's always a right angle there, right? Okay. So when I do this, when I take a ray that goes through the center of my circle, okay, and intersects my tangent line over here, okay? So I draw that ray, but I'm actually going to do it this way, because I'm going to use, instead of a ray, let's use the entire line. What do you guys know that line is referred to as for a circle? Or maybe not that line, but that segment there is a what, Carter? Okay, so that blue line is a diameter. If I extend that blue line as a segment, okay, so I'm talking now about, extend it as a line. So take that dark blue segment or that thick blue segment, extend it as a line. This line is called a secant, okay, a word we've heard before. But when we do this, it should intersect our tangent line over here. No matter where our tangent line is, would you agree that unless the tangent line and this thing are parallel, which only happens once, would you agree that this line here and this line here are going to intersect?
Yes, sir.
Okay, when they intersect, okay, we get ultimately that triangle right there, correct? What type of triangle is that?
45, right.
Yeah, the
90-degree triangle.
the safest thing to say is that it's a right triangle. Okay, I don't necessarily know.
Do the clicking thing and find out.
Huh?
Do the clicking thing and find out the angle.
It's not going to be a 45, 45, 90. Why we call this a tangent is because if I look at this distance right here, which is a portion of the tangent line, right? Okay. And I divide it by, I didn't want that one to be that color. All right. So then if I take, Okay, so I take the pink segment and divide it by the purple segment. That should give me the same exact ratio of the tangent of 64.39 degrees. Okay, so let's see if that happens. If I take, let's see what these, so this would have been, all right, so A sub 1 divided by that segment there, which is F. Okay, so A sub 1 divided by F, it gives me the number 2.09. Okay, so that's taking this segment, this pink segment, and dividing it by the purple one. Okay, is that the same thing I get when I take tangent of 64.39?
Yeah.
64.39, plug that in there, 2.09. Does that kind of make sense, everybody? So the length of this thing here, the length of that segment, which is a portion of your tangent line, it's your tangent segment, okay, is exactly the same as the tangent of this angle that's created by that triangle down here in this circle. And I can change the circle size, and we see it that stays the same, okay? Now what we really like to do, guys, is we like to change our circle size so that our radius is 1. Will you stop, please? So our circle is 1, okay? And if my circle has a radius of 1, then this side right here is 2.09 divided by 1, which is just 2.09, which is exactly the same thing as I get when 64.39 run through the tangent formula, or tangent ratio. And that is true no matter where that tangent line or tangent point goes, okay? But this side right here is 1.35, okay? 1.35 divided by 1 gives me 1.35. Now, don't worry about the negative. We'll talk about that in trigonometry class. But that's the relationship that exists between the tangents that we talked about in chapter 7 and 8 to the tangents that we're talking about now, okay? Whether you need to know that in detail and how to do that, I don't think you do right now, but it is something we talk about later on in other courses. Yes?
So, like, it's just like pointless finding like the B to B side or whatever. Like, ours is just supposed to like know like tangent 64.39.
No, you don't need to know any of those things right now, because all I'm trying to do is try to get you to realize that this line right here, the reason we call it tangent or a tangent line is the relationship between it and the right triangle that's created when I extend that ray through here, through that center. Does that kind of make sense? So I just want you to see if there's a link between what we've already done and what we're doing now. Okay. In the past, people said, well, they're different. It's the tangent for right triangles, and then it's the tangent for circles. They're the same. Okay. What we're going to kind of work on in this chapter is all the properties that exist between circles and this tangent line. One of those properties is that this radius is always going to be perpendicular to that tangent line at the point of tangency. Okay, so that's important. Now, the other part that is important, we are talking about the exactly 1 point being a necessity. In the plane of the circle is another phrase that is important for this reason here. If we show some stuff going on here, would you guys agree that if I look at a three-dimensional rendering of a circle, I just put it in a different plane, I've raised it, in that blue line, they are in the same plane. If I look at that plane right there, would you agree that both those shapes are in that teal plane?
Yes.
Okay, so we call that blue line a tangent line. Okay, now, is that red line, does that intersect my circle one time? Yes. But is it in the same plane as the circle? Is it in the teal plane? No. Okay, so that red line, even though it intersects my circle one time, it is not a tangent line. Does that make sense to everybody? Okay. So there's a discrepancy between the blue one is a tangent, the red one is not. So when I ask you like an always, sometimes, never, or true and false question, I say this is a line that intersects a circle one time, and I say that that's a tangent line, that's false. Okay? Because that red one is a line that intersects a circle one time. There's more to the definition. Does that make sense? Okay? Because we don't have all of the same characteristics with that red line in the circle that we get with the red or the blue line in the circle. Does that make sense? So we want to have a definition that eliminates that red line, and putting in that phrase "in the same plane" does that for us. Okay. So those are key phrases to think about when we talk about those definitions. This like I said, this is always going to be true. Your radius and your tangent line are always going to be perpendicular at your point of tangency, and that gets asked a lot, or you deal with that a lot in a lot of the problems that they ask throughout this chapter. If I look at LM, or ML, I guess, and MN, they are tangent to circle O. Okay, that's how we define or write circle of whatever. Okay, so O is the center, so we write circle O. What kind of angle do we have at L if this is a radius and this is a tangent line? What kind of angle is L?
Right angle.
Right angle. What kind of angle is N?
Right angle.
A right angle. How many degrees are there in that green shape? 360. Okay, every quadrilateral is 360 degrees, right? We have, so 360 is our total. If I remove from that 90 and 90 and 117, what will that give me? Or what angle will that give me? Give me X, won't it?
Yeah.
Okay. So that's something that we get asked a lot. Can you take a circle and we got some tangents being attached to that circle? Can you use the relationship that we know a tangent and a radius are perpendicular? And then that should kind of open the door for us to use other geometry that we've learned so far. Okay. Other questions that kind of stem from that are, kind of like this. Very similar. Instead of now a quadrilateral, this is a triangle. So what kind of angle do we have at D? If DE is a tangent, it's a right angle. So now we're looking at this right triangle. How many degrees are there in a right triangle? 180. So this angle here and this one here have to be complementary. So does that make X equal 52? Is this something we can do with those? Okay, so you see quite a few of those kind of playing off the, ultimately playing off of the n-2 times 180 concept that we learned in chapters, 6 and 7. You're also going to see them play off of the Pythagorean theorem a little bit. So I'm going to actually go to this slide here, do this example with you first. They're going to ask you, look at this picture, is ML a tangent line? Okay? And the question is, if it is indeed a tangent line, what kind of triangle would this have to be? A right triangle. Those would have to be perpendicular there. So which theorem about triangles deals with right triangles a lot? Right? We use a lot, that we're most comfortable with. Right. We know a squared plus b squared should equal c squared, right? What is an option for A in this picture? 24. What is then B? 7. And C would have to be 25. We want to see, is this true? If it's true, this is a right angle, right? Okay. If c squared is bigger, this would be an obtuse angle. Okay, or if it's smaller, this would be an acute angle. And that would ultimately tell me that that line intersects either no times or 2 times. Okay, but if it's equal, it tells me that this line intersects exactly 1 time with the circle. So what's 24 squared? Anybody know? 576. Okay. 7 squared is
49.
49. Anybody know 25 squared? Good, 625. Is that a true statement then? Does that sum equal 625? Yes, it does. So it's a true statement. So Pythagorean theorem is true or works. And what kind of triangles does the Pythagorean theorem exist for? Right triangle. So this must be a right triangle. That must be a right angle. Then ML must be a tangent line. That kind of make sense? Okay. So that's a version of kind of the Pythagorean theorem that they're going to ask in your homework. But in order to kind of address it, they're asking, do you understand the idea that a radius and a tangent line need to be perpendicular? Okay. So that gets us to another style of Pythagorean theorem question with this stuff. And this one, people make 2 mistakes. Okay, so I'll make sure we cover at least one example of this. They want to find the radius. So if I look at this, they want me to find x, right? That length. Okay. If this is a right triangle, and it is, they tell us that this is AB is a tangent line. What would be an option for like a squared or b squared when I look at this thing? What could a be? It could be 12. So if a is 12, what's b got to be then? X. Okay? So usually people get that side correct. What is the other side? What is the hypotenuse going to be here? 8 plus x. Okay? The number one error I see there is that people put 8x. Remember, it's addition to go from there to there. I've walked x units, and then I've walked 8 more on top of that, right? So x plus 8. This becomes 144 plus x squared. What's the right-hand side become? And that's the number one error I see.
No.
Because what does x plus 8 squared mean? What does anything squared mean? Times it by itself. So x plus 8 squared means x plus 8 times x plus 8. And what do you do with that?
No.
Careful.
Foil.
Foil. So first times first would give me my x squared, right?
Yeah.
Last times last would give me my 64, right?
Yeah.
What are we missing? 16x. We're missing O and I. Okay? So that's something that we miss a lot, okay? And this idea here that x plus 8 squared is the same as x plus 8 times x plus 8 is one of the number one things on an ACT or the end of course exam that the author will try to get you on, okay? Because most people, especially only having Algebra 1 by the time you're taking these tests, most people want to say x squared plus 64 is that product, okay? We need to be careful with that. So then solving this should be pretty simple, pretty straightforward. What's going to happen with my x squareds?
Cancel out.
Cancel each other out. So now it's just 144 is equal to 16x plus 64. Subtract 64 from both sides. Divide by 16. X is 5. So now we have that circle that is defined by a radius of 5, whatever, 5 inches, 5 feet, 5 miles, whatever you want to be.
I don't know if my window's down.
Okay. You can have a soggy ride on the way home. All right. Let's talk about some other features of these tangent lines. I guess the first thing we should probably talk about is the fact that the converse of that theorem that we've already talked about is true as well. So we know that a radius and a tangent line are perpendicular. The other thing that we know, or that we can do, is take the converse of that. So say that you start off with a line like AB, and it's perpendicular to a radius, okay? But now it has to be perpendicular to the radius at the radius's endpoint, okay? So if we know that that's the case, if we know that right angle exists at P, then we can classify that red line as a tangent line, okay? So if you start off with the knowledge that you have a tangent line and a radius, then you know they're perpendicular. Here it says if you start off with a radius perpendicular to some other line at that radius's endpoint, then that other line can be classified as a tangent. And it's ultimately the converse of that first theorem we talked about. Okay. Now the key thing here, the key phrase, is that right there. A lot of people think that's not important. Okay. But if I kind of construct a picture for you here real quick. Computer's been slow today. All right. All right, so if I put in a line that is perpendicular to that one, perpendicular to AB, okay, would you guys agree that the blue line is perpendicular to AB?
Yeah.
Does it meet the definition of a tangent line, though? Because why?
It goes through twice.
It goes through twice. So we have to move that point out, okay? There's still a right angle here, right? But we have to move that to where that point C becomes point B, so now it's at the end point, and now that's a tangent line, right? Is it a tangent line at that end point?
No.
No. It's got to be a tangent point at that end point, or perpendicular at that end point, and therefore that blue line now becomes a tangent. All right, so that being said, let's talk about another fact. And let me just close some stuff out here because this is really slow because of all the things I've got open. All right, one of the kind of most important theorems that they ask about or they deal with is looking at looking at a circle with two tangents. Okay, every single circle, if I choose a point outside the circle, it's going to have two tangent lines that can be drawn from that point to the circle. Okay, no matter what circle you ever deal with. So small circle, big circle. Okay, now that one they disappear because that point C is on the inside of the circle now, right? The point has to be on the outside, but you can always, no matter how big your circle is, you're going to have two tangents can be drawn to it. Is that okay with everybody? Okay. Now, if we focus, because I can't find the length of the entire tangent line, because lines go on forever, so you can't find its length. But if we look at from that external point C to the point of tangent C, on both those tangent lines, what do you think you can tell about those two dotted lines? They're the same, okay? And if we look down here, there are these two blue numbers right there. No matter where I move C, okay, those two values are always identical, right? Okay, and that's what this theorem is getting at. It says, let me find where it's at. Right here. If two tangent segments to a circle share a common endpoint, so in this case, that point B, then the two segments are congruent. So those two red segments are the same length. And that's what we're seeing here. But I want you guys to recognize why this is true. Okay? If this is a tangent line, or a portion of a tangent line, that's point D is a point of tangency, right? A to D is a what? Radius. So what kind of angle do you have here at D?
90 degrees.
You have a 90-degree angle there. Okay, so put that in, got a right angle. Would you agree that this is another radius.
Yes.
So what kind of angle do you have here at E?
90 degrees.
90 degrees again. Okay. What would you say about those two radii in relationship to one another? They're the same. Okay, it's the key relationship about ultimately all radii of the same circle, right? Those two distances. Apologize real quick. That's canceled.
Oh, that was lightning, coach.
All right, so we know those two distances are the same, correct? We know these two angles that are green, they're both right angles, they're the same. Would you guys make the argument that that segment is congruent to itself?
Yeah.
Okay, so if that's the case, all right, let's look at the red segments. Okay, this is a right triangle up top, right?
Yep.
It's a right triangle on the bottom, right?
Yep.
Okay. Is that a leg? Is that red segment a leg for this right triangle?
It is.
Okay. And it's a leg for the bottom one, right?
Yep.
What's the purple line for both triangles?
Another leg.
It's across from the 90 degrees.
Oh, it's
Angle bisector.
It's a hypotenuse, isn't it?
what? Oh, I got the other one.
It's across from the right angle. Okay. So that purple dotted line is the hypotenuse. The red ones are legs. What's that tell you about these two triangles?
Yeah, congruent.
They're congruent by hypotenuse leg. So if they're congruent by hypotenuse leg, then all the corresponding parts that we haven't talked about should be congruent by CP, right?
Yes.
Are those blue segments corresponding parts?
Yes.
You betcha. Okay? So that means by CP, those two blue segments are always 100% of the time, no matter where C is, as long as it's external. Okay? Those two segments will always be congruent. But the reason I show that and I wanted that proof is, what was the number one thing that got us to this relationship? What kind of shapes?
Triangle.
Triangles. Okay? So triangles tell us everything we need to know about the segments that relate to circles. Okay? All right, so the next thing they're going to ask you to do is something like this. They're going to, we've talked about this phrasing before in the past. Okay, we've got this circle on the inside. Okay, in each one of these green segments. Okay, so that green segment, would you guys agree that that's a tangent segment?
Yes.
Okay, would you agree that that dotted one is a tangent segment?
So,
This one over here,
yes.
tangent segment, and that dotted one there is a tangent segment as well, right? When you have a circle that is enclosed by a series of tangent segments, okay, that circle is drawn on the inside. We refer to that as an inscribed circle, okay? But the shape on the outside has to be tangent on all of its sides. Does that make sense? Okay, so I can't have, and the way I constructed this, I don't think I can show this, but I can't have maybe this side here intersecting the circle twice. Okay, every side has to be touching one time. And I cannot have, now maybe if I, it's going to kind of look ugly, but okay, I cannot have a shape like that. Let's see if I can delete that, show object. Okay. That quadrilateral, or whatever you want to call it, would not be what we refer to as circumscribed, because this side here is not tangent to the circle. Does that make sense? All sides have to be tangent to the circle. So that shape right there, the quadrilateral we say is circumscribed. The circle we say is inscribed. Okay, and those are terms that we've used before. Okay, but now we're actually defining it and adding into the definition the idea of tangency for it. Okay, we talk about these with circumcenters and orthocenters and that kind of stuff. We did the in-center. The in-center provided the inscribed circle. The circumcenter provided the circumscribed circle, okay? Now we can talk about it using the tangency concept, okay? So in that triangle up top in that first picture, each side of that triangle is tangent to the circle. In the quadrilateral, each side of the quadrilateral is tangent to the circle. Therefore, the circle is inscribed, and the polygons are referred to as circumscribed. Okay? Just some terminology that's going to be used throughout the rest of this chapter and the rest of the course. And that brings us to the last thing I want to talk about, and we should be able to kind of wrap it up pretty quickly. If I'm talking about two circles, okay, and I don't care the size of the two circles, but let's just say that they are not touching. Okay, so these circles are not touching, which is a nice thing. I should be able to draw tangent lines that are common to these circles. Common meaning they share them. Those are all the tangent lines that we can share. Okay, now I want to just look at the two on the outside. Okay, those two are referred to as external tangents. Okay, that makes sense? Okay. Something that we like to deal with in regards to external tangents, and maybe, I know Tyler, you're probably familiar with this because you work with automobiles. If we just look at the the tangent lines that connect those two circles, okay? Do those look like maybe the pulleys or like the serpentine belts or whatever on an engine, okay? Or the gears on a bicycle and the tangent being the chain, okay? The lengths of those things are directly related to the circumference of the circles and the distance the circles are from one another and the lengths of those tangent lines. Does that kind of make sense? And we can do a lot of stuff, and we'll see maybe an example of how we can kind of use this geometry in a real-life situation with, belts on an engine or chains on a bicycle or something like that. So those are maybe an application of what we refer to as external tangent lines, common tangent lines. These are referred to as your internal tangent lines, okay? And ultimately, if I just look at just one of those, would you guys agree that kind of one of the circles is on one side of the line, the other one's on the other side of the line? Okay? That's how you kind of identify. The definition says you identify them by saying that if your tangent line intersects the imaginary line connecting the centers of your circles, then it's an internal tangent. I think you're going to find out that it's kind of easier to look at one circle on one side of the line, the other circle on the other side of the line, and that classifies that black line as a common internal tangent. Okay. The last few slides of the PowerPoint are probably maybe something you want to look at because they give you all those varying different tangent lines and how circles can become tangent and stuff like that. Might help you a little bit in your homework. We'll talk about it at the beginning of class tomorrow again. But there is an assignment on Math Excel. Due tomorrow.
What? Craig. All right, Craig, how many questions?